Hi students, welcome to Physics for Everyone classes. This is your Satish sir. If you're watching this channel for the first time, please subscribe. In this video, I'm dealing about the significance of the Lenz law, which is very short but the most important. In the Lenz law, actually we found the direction for the induced current. We haven't discussed about how the induced current is developed. Here, I'm dealing the why the induced current is developed inside the closed coil when there is a change in magnetic flux. Let us see. Here, I'm taking the magnet which is moving towards the closed coil. As we have seen, when this north pole is moving towards the coil, the face of the coil comes as the north pole. And between these two same polarities, there we can expect a repulsion between the coil and the magnet. Repulsion means some opposing force is acting on this magnet in the opposite direction to its motion. We can see about the center of mass, we can draw some force is acting in the opposite direction in this way. But we need to move the magnet towards the coil in this manner, towards the coil, opposite to this opposition force, which means we need to apply some external force in the opposite direction to this opposition force. You can take about the same point. I'm applying some external force in the forward direction, named it as Fe. You can see clearly where Fe is the opposition force on this magnet due to the current carrying coil, which itself acts as a virtual bar magnet. Now, to move this magnet in the forward direction, we need to apply the same amount of force in the forward direction. Now, what will happen? These two forces are equal in magnitude but opposite in direction. They cancel each other. But due to the tendency of the motion of the magnet is moving in the forward direction with a constant speed v. Here we are doing some the external work done. Isn't it? Yes, because some force is there and the magnet is moving forward but covering some displacement. When force and displacement both are existing, there is a certain amount of work is done on this magnet, and this work is converted into electrical energy inside the conducting coil. So this obeys the Lenz law obeys the law of conservation of energy. You might think in this way: the magnetic energy is being converted into the electrical energy, which is false, because even when the magnet is at rest, the magnetic lines of force are passing through this coil. But in this situation, you are not getting any induced current. So how we can say that the magnetic energy is directly converted into the electrical energy, which is the false statement. So what exactly means that here we are doing some external work on the bar magnet. So this work is being converted into electrical energy. Suppose here the question has been asking like this: how much is the force is acting on this bar magnet? in terms of the distance between the magnet and the coil. This has been very easy. We are using all the fundamental results to find the magnitude of force acting on this bar magnet. And this was the question which is given in the JEE Advanced. So I'm trying to find the force acting on this bar magnet due to the opposition. So if I to find the force, the last step, we need to start our journey from magnetic induction created by this bar magnet at a distance x. You see here clearly, at a particular instant of time, I'm taking the distance between the magnet and the coil is x. Now at x distance, we can easily find how much is the magnetic induction created by this the short bar magnet on the axial line. We can use the direct result which is in magnetism chapter. And the second step is, after getting B, we can find the flux which is passing through this coil. Phi is the second step. After getting flux, we can easily find out induced EMF from the Faraday laws. First one is magnetic induction due to bar magnet. Second step, the flux passing through this coil. The third step, induced EMF created in the coil. And the fourth step is to find the induced current by using Ohm's law. I is equal to V by R. And next one is after getting the induced current, and this one is been acting like a virtual bar magnet, and for its the magnetic moment is being taken as m dash, where m dash is the magnetic moment of this the current carrying coil. After getting the magnetic moment, we can find how much is the potential energy is being stored of this the current carrying coil, the potential energy of this bar magnet, virtual bar magnet. So you can use the symbol U, potential energy. And there is finally a relation between the force and the potential energy. With that, we can get the how much is the force acting on this bar magnet, how much is the force which is required to move this magnet with a constant speed. Those are same actually. So this is the long journey, but we are using all the direct results to get the force related to the distance between the magnet and the coil. Let us start. The first one is magnetic induction of the bar magnet. How much it is, which is given as B is equal to mu naught by 4 pi into 2m divided by x cube. This is a very standard result in the magnetism. For a bar magnet, for a short bar magnet on the axial line at a distance x, the magnetic induction is given by mu naught by 4 pi into 2m by x cube. And the magnetic flux which is given by phi is equal to BA, and the angle between these two is 0 degree there, because the magnetic field is along x-axis, and a variable vector also you can take perpendicular to the surface along the x-axis. So directly you can write the maximum flux is passing through the coil, which is BA. So you need to do directly put the B value in this equation, and taking area is equal to pi into A square, because A is taken as the radius of the coil. Right on. B is equal to mu naught by 4 pi into 2m divided by x cube. A, area of cross section of this coil. How much it is? Yes, it is pi into A square, because it is in a circular in manner. We got the flux passing through the coil. So how the flux related with the distance? They can write phi proportional to 1 by x cube, where x is decreasing and the flux is increasing in the huge manner because it is the cube of the distance. So after getting the flux, the next one is the induced EMF in the coil. So we come across Faraday's law, the second law. What it is given? E is equal to minus d by dt of flux. The rate of change of magnetic flux is equal to the induced EMF in the coil. So take this entire expression here and you take the common things will get cancelled. The one is 5, the second one is 2 times get cancelled, and take this expression here which is equal to minus d by dt of how much is 5? Yes, mu naught into m, the magnetic moment of the bar magnet, into a square divided by 2 into x power 3. And differentiation with respect to time. Here no time related terms is not there. Only the position is a variable. So be careful. If you differentiate this with respect to time, finally you will get the result in terms of velocity. How? Let us look. So initially take all the constant values outside. Mu naught constant, magnetic moment a square constant, to be constant. Take outside. So minus of mu naught m into a square divided by 2. In bracket you can write it as d by dt of x power minus 3. And derivative of the x power n. What's the formula? So there I can write d by dx of x power n, which is equal to n into x power n minus 1. Be careful where we are derivating x with dx. So this equation is being used. But here we are finding the differentiation of x variable with respect to the time. So at last we need to take dx by dt also, which is nothing but the velocity of this magnet. So let us see. So minus mu naught m a square by 2. Use this formula simply. Here n comes as minus 3. So minus 3 into x power n minus 1, which is my x power minus 3 minus 1. Is it over? No, because this is in terms of x, here it is in terms of time. So you need to extend one more term, which is dx by dt also. Don't forget this term. As here the variable is x and differentiating with respect to x, you will get this one, n into x power n minus 1. The variable is x, we are differentiating with respect to time, you will get n into x power n minus 1 into dx by dt also. So take care of this, the last expression, which is nothing but dx by dt is nothing but the velocity of the bar magnet. And finally you will get which is equal to minus becomes positive. You can write 3 times of mu naught m into a square divided by 2, and this expression comes as 1 by x power 4 into this one comes as v. What is v? That's velocity of the constant speed of the bar magnet. And we have reached induced EMF again, which is proportional to E proportional to 1 by x power 4. All the remaining terms are constant. V itself is a constant because how much opposition is there, we are applying the same amount of external force for making the magnet is moving with a constant velocity. Yes. So mu naught m a square 2 3 v, everything is constant. The only one thing is that as the magnet is approaching the coil, here x is decreasing, with that induced EMF increases. And take a pause. note down clearly one by one step on your notes. Okay. So after getting induced EMF, we to find the induced current. This is a very simple. By using Ohm's law, we can get that. So I'm taking here the last result, which is induced EMF here. How much? This expression. And here is the induced EMF. This is. So for to find the induced current, by using Ohm's law, we can write I is equal to V by R. What is R? Where R is the resistance of this coil, capital R. So that is equal to, and take this entire expression divided by resistance, you will get the induced current, nothing else. So 3 into mu naught M into A square divided by 2 into x power 4 into V, and divided by the resistance of the coil. There you will get the induced current. And the next step is to find the magnetic moment of this current carrying coil. And for this, you can write M dash is equal to, so you know the magnetic moment of the current carrying coil, which is given as the current into area of cross section, the induced current into the area of cross section of the coil, that is equal to, check the entire thing. So 3 mu naught M A square V divided by 2 into capital R into x power 4 into, what is A? Already used. So pi into A square. You see here, A square into A square. It comes as A to the power of 4. So 3 mu naught M V into pi into a power 4 divided by 2 into x to the power of 4. So we got magnetic moment of the coil. And the next one is the potential energy. What it means? If any bar magnet or a virtual magnet, if it is placed in the external magnetic field, a uniform external magnetic field, there exists a potential energy which is given by U is equal to, the result is minus mb into cos theta. So what is M here? The magnetic moment of this coil, which is taken as M dash. So right here M dash. What is B? The magnetic induction of this bar magnet at a distance x. Already we know this one. And theta is the angle between these two. So how much is the angle? As the induced current which is set in this coil is anti-clockwise direction, like this, by the thumb rule, M dash is acting in negative x-axis. You can take this is negative x-axis. But B is a magnetic induction due to this bar magnet is acting along positive x-axis. So the angle between these two is equal to 180 degree. So you can take here, so minus M dash B into cos 180, which is minus 1, and negative negative get cancelled, which is equal to M dash into B. What is MP? It is not Mahesh Babu. It is the magnetic moment of the coil, and the B is the magnetic induction of the bar magnet. Now take M dash expression here and B also, and finally you will get U is equal to 3 mu naught M V. V is the velocity, pi a power 4 divided by 2 into R into x power 4 into, what is B? Coming to the first equation, which we are taking as mu naught by 4 pi into 2m by x cube. Very big expression. You manage to get all the things in simpler way. So you take here, almost everything is constant except the distance. You write here. So what I can take here, 3 2, 6, and 2 get cancelled here. 2 get cancelled, and m into m square, and mu naught into mu naught. So we can write mu naught square. So 3 into mu naught square, and we can take here m square into velocity, and next one is pi, 1 get cancelled, and above everything is known. So 3 mu naught square m square into v into a to the power of 4 divided by capital R resistance into 4 is there, and x power 4 into x power 3 is x power 7. You got this much. So potential energy is equal to how much you got? 3 mu naught square m square v into a power 4 divided by 4 r into x power 7. And the relation between the potential energy and the distance you got here it as u proportional to 1 by x to the power of 7. If x decreases, potential energy increases a lot. You can say x power 7 inversely. So we reach almost the last step, which is to find the force acting on this, the opposition force acting on this bar magnet. So take the last expression. So F, the opposition force or the external force, which is equal to how this one is related to potential energy. Yes, here the magnetic field, which is a conservative field, in that field we can use the relation between the force and the potential energy, which is known as F is equal to minus du by dx, and that is equal to minus d by dx of potential energy. The entire thing you can take. Everything is constant, right? Except x power 7. Directly you can take the constant outside and take only the variable inside, which is x to the power of minus 7. And the constant I can take it as minus something k. I can write here the side where k is equal to everything, which is equal to 3 mu naught square m square a power 4 into v divided by 4 into capital R, which is constant, and that is equal to minus k into and d by dx of x power 7. Here the variable is the x and we are differentiating with respect to x. Directly you can use n into x power n minus 1. How much is n? Minus 7, right? And x to the power of minus 7 minus 1. And here there will be no any extension. That is equal to minus minus will get positive, so it comes as k into 7 divided by x to the power of 8. And we reach the result, how much? This one. So 7k divided by x to the power of 8, where k is equal to this much. If you take this k here and multiply and write the entire equation, or else you can get the relation between the force and distance. F is proportional to 1 by x to the power of 8. You can see the relation. If x decreases, the force increases very much as compared to the remaining all the other parameters, where we have seen p proportional to 1 by x cube, or something like flux is proportional to 1 by x power 4, or E is also same thing. I is also same thing, magnetic moment, but potential energy is proportional to how much I wrote here, 1 by x to the power of 7, and finally the force comes as 1 by x to the power of 8. So all these relations are really important regarding the NEET as well as the JEE examinations. I'm not asking to by heart all the relations, all the equations, just you focus on these relations, how B related with the distance or flux related with the distance, or induced EMF current, magnetic moment, potential energy, or the force are being related with the distance between the magnet and the coil. And you might get some conceptual questions related to this one. So thank you very much. And if you're watching this channel for the first time, and kindly subscribe the channel and also support the channel.